title of my talk today has to do with synthesis and applications of certain polycyclic cage compounds as high energy density materials. So, if you go back to history more than 2000 years ago, Plato has predicted that there are only 5 geometric figures that can have identical convex faces, and those are tetrahedron, cube, dodecahedron, octahedron, and icosahedron. Now, only 3 of them can have hydrocarbon analogues due to valency restrictions: tetrahedron, cubane, and dodecahedron. These geometric figures have remained an academic curiosity until recently. Only in the last couple of decades, cubane has been projected as a high energy density material, and it has also been used as part of a chiral ligand and also attached to medicinally active compounds. And this octanitrocubane is considered to be is a highly energetic, explosive. Now, we have had interest in the chemistry of polycyclic cage compounds, particularly the bis-homocubanes, with 2 additional carbons compared to cubane. And we have investigated an equilibrium between cage vinylidene carbene and its corresponding acetylene, and found that the carbene is both kinetically and thermodynamically more stable than acetylene, thanks to the enormous strain that is present in the molecule. Unlike the open chain systems where the carbene spontaneously rearranges to the corresponding acetylene. Now, I'll focus today on the energetic properties of cage compounds. As you know, energetic materials are used both civilian and defense applications. Although we have carried out the synthesis, many of the properties were evaluated by my collaborators, the combustion engineers, Professor Arindrajit Chaudhary and Neeraj Kumbhakarna from Mechanical Engineering Department. Again, if you go back to history, this is chronology of energetic materials. China has used black powder for the first time, and then Nobel developed dynamite. And TNT has been used as first generation energetic material, and RDX and HMX are extensively used. And these are the 3rd generation nitro compounds like Cl20, octanitrocubane, and also hydrozinium nitroformate and ammonium dinitromide. But none of these have been scaled up for practical applications. So what are the basic requirements for a compound to exhibit energetic properties? As far as propellants are concerned, we look at the specific impulse. Specific impulse is basically the thrust or the impulse delivered per unit propellant consumed. So it is F by M, and it is expressed in seconds. Now, if you multiply specific impulse with the specific gravity of the mixture, then it is a density specific impulse, rho specific impulse, which is particularly important for high dense materials like the cage compounds. And if you take the standard RP1 rocket propellant fuel, the ISP is 366.2, but rho ISP is slightly higher, and as a liquid propellant. And if you consider solid propellants like ammonium perchlorate, HTPB mixture, where HTPB is binder, ammonium perchlorate is the oxidizer, the ISP is 275, whereas rho ISP is 438. Now, other properties are important as far as, for explosives like oxygen balance and detonation pressure, detonation velocity, burn rate, heat of formation, ignition characteristics, etc., and various thermal and mechanical properties. So initially, we have compared the properties of conventional hydrocarbons with cage hydrocarbons. As you can see here, conventional hydrocarbons have negative heat of formation, low density, no strain, whereas cage compounds like cubane have high positive heat of formation, high density, and high strain energy. In spite of that, such compounds do not undergo decomposition. Therefore, cubane-like compounds are considered as kinetic rocks, but thermodynamic powerhouses. And where does the energy come from? The energy comes from the angle strain. As you can see here, cyclopropane has the highest angle strain, and the heat of combustion per methylene is highest for cyclopropane. So if you have cubane-like compounds with several cyclobutane rings fused, in addition to angle strain, there is torsional strain as well, which is stored in the structure of the molecule. So these are some of the properties of cubane: high melting, high boiling, low decomposition, high density, high vapor pressure, high positive heat of formation, enthalpy of sublimations, strain energy, etc. So, these are the properties expected of such cage hydrocarbons: faster ignition, higher heat capacity, superior burn rate, greater heat release, at the same time kinetic stability compared to conventional fuels, and these do not require any cryogenic conditions for storage, and these are also less sensitive. So initially we have calculated the heats of formation and specific impulse of cubane and several other hydrocarbon materials. As you can see that cubane has the highest, all of them have high positive heat of formation. Cubane has the highest specific impulse, followed by methyl cubane, and then other cage hydrocarbons also have high specific impulse. And we also notice that if you take the dimer has higher specific impulse compared to monomer. For example, this bis-homocubane has an ISP of 365 seconds, whereas its dimer has 371. So there is a 6 seconds improvement in terms of specific impulse. So considering that, we have synthesized this bis-homocubane dimer in 4 steps, starting from readily available dicyclopentadiene in excellent overall yield, and found that these have, this has high positive heat of formation and also ISP much better than that of conventional hydrocarbon fuel, the rocket propellant fuel RP1. At this point, the VSSC scientists have advised us to introduce energetic functional groups like nitro, azido, and so on to such cage hydrocarbons, because there was some precedence in the literature. Tris-homocubane, the tetranitro tris-homocubane was considered as, was less shock sensitive than TNT. At the same time, it has an energy output comparable to that of an RDX TNT mixture. Similarly, octanitrocubane is more powerful than HMX. But synthesis of these compounds on a large scale for practical applications is a challenging task. Therefore, initially we focused on bis-homocubane skeleton with 2 additional carbons compared to cubane, which can be prepared in a couple of steps, starting from readily available dicyclopentadiene. So this cage diol was synthesized, which was then nitrated to get this dinitrate. And as you can see here, the dinitrate has a raw ISP of about more than 45 seconds higher than that of RP1. And we have also converted this bis-homocubanon to several nitro derivatives, both unsaturated and saturated, and also the one containing 2 nitro groups. And in all the cases, you can see the specific impulse of the RP1. So here these compounds are added to RP1 about 30%. That improves the specific impulse by about 20 to 76 seconds. And if you add these compounds to a solid propellant combination like AP, ammonium perchlorate HTPB, or replace HTPB with these compounds, then also the specific impulse is much higher, about 25 to 30 second improvement. We have again prepared this cage diol in good quantity and converted it to this bis azide, which was then converted to this bis triazole and also this bis tetrazole. And you can see that addition of 30% of any of these compounds to RP1 would improve the specific impulse by about 14 to 83 seconds. And also replacing HTPB in the solid propellant combination would also improve the ISP by about 20 to 35 seconds. And even though there are more number of steps involved in the synthesis of homocubane, that is one carbon homologue of cubane, we synthesized this homocubane carboxylic acid in about 6 steps, and then looked at its ISP. So as a liquid propellant, this would perform much better than RP1, more than 19 seconds improvement. And as a solid propellant additive, also this would perform with very high ISP. And we have also synthesized several other derivatives, which are, of course, not that energetic. And we converted this homocubane carboxylic acid to several derivatives like this methyl homocubane, hydroxymethyl cyano tetrazole derivative, and also oxadiazole. So in all the cases, these compounds performed well as a liquid propellant additive, 30% to RP1, and also as a substitute for hydroxy terminated polybutadiene, that is HTPB. And we have also converted the homocubane carboxylic acid to its ester and another oxadiazole and this hydrazide and also this amino oxadiazole. In all cases, the ISPs are much superior compared to RP1 and in liquid propellant combination, and also compared to HTPB in the solid propellant combination. Now, we also converted the hydroxymethyl homocubane to this triazine, and also this triazole, amino triazole containing 2 homocubane moieties. And in both cases, you can see the, these 2 compounds perform much better compared to conventional liquid propellant RP1 and solid propellant binder HTPB. And so at this point, we thought that even though it takes several steps to synthesize cubane, it takes about 8 steps to make this cubane dicarboxylate. We prepared it, and we thought we would evaluate the cubane derivatives as well. And we have synthesized this tetrazole, monotetrazole, and also this bis oxadiazole. And in both cases, as a liquid propellant and also as a solid propellant, these compounds performed much better. As liquid propellant, more than 27 to 33 seconds improvement, and also as a solid propellant, very high, more than 100 to 140 seconds improvement compared to HTPB. Finally, we went back to bis homocubane because it's easier to synthesize in a couple of steps from dicyclopentadiene. So we prepared this cage keto alcohol, which was converted to this dinitrate, and also this keto nitrate, dinitroalcohol, azide, and also this trinitro compound, dinitro nitrate. And as highlighted, you can see that these compounds perform well as liquid propellant additive with about 20 to 30 seconds improvement, and also as solid propellant substitute for HTPB in solid propellants. The cage keto alcohol was also converted to this keto azide, and by accident we have got this cage dimer when we attempted to reduce the azide group, and this amide was also isolated as a side product. And all these compounds have shown much higher specific impulse, both as a liquid propellant additive and also as a substitute for HTPB in solid propellant. So these are the compounds we have synthesized and evaluated, and these are the bis-homocubane derivatives, and here we have the homocubane derivatives, and couple of cubane derivatives also have been synthesized, and evaluated, and their performance in terms of ISPs are shown here. And so as I told you in the beginning, we have carried out synthesis and characterization of these compounds. The thermal analysis, calculations, all the decomposition pathways were all carried out by our collaborator in the mechanical engineering department. For instance, the thermal decomposition was investigated by using TGA, And the gaseous products were analyzed by rapid scan, FTIR, and mass. And the decomposition pathways were evaluated by DFT ab initio, and the compounds were also, the structures were also optimized using DFT. And the propulsive properties, especially the ISPs, were calculated using a software called NASA CEA. And these properties are not important for our compounds because our compounds are not explosives. But the challenges involved are the scale up. Still, there are many steps involved to synthesize these compounds in reasonable scale, and the number of, we try to minimize the number of steps as much as possible. Also, since these are hydrocarbon derivatives, soot formation is a problem which has to be addressed. And again, our collaborators have evaluated representative compounds, for example, this dinitro compound, and found that addition of this dinitro methyl bishomocubane to RP1 enhances the burn rate by promoting micro explosions. And also addition of this bis tetrasol, bishomocubane derived bis tetrasol to AP HTP mixture, only 5%, addition of 5% is enough to improve the burn rate by about 15 to 20%. The red dots are for the cage, added mixture, and the black squares are for the conventional AP HTPB mixture. So our, we are trying to improve the performance of conventional fuels, liquid propellants like RP1, and also the solid propellant AP HTPB mixture by, adding our cage compounds as additives. So we, this is one of our interests, the application of polycyclic cage compounds as energetic materials. We also have interest in other, for instance, development of new synthetic methodologies, mechanistic studies, and synthesis of other materials with interesting properties. And quickly, some of our properties are, some of our projects involve alpha functionalization of nitroalkenes under the Morita-Baylis-Hillman and Rauhut-Carrier conditions, synthesis of polynitrogen containing heterocycles using diazo compounds, especially Bestman Ohira reagent, catalytic asymmetric conjugate addition of active methylene and methine compounds to electron deficient alkenes, synthetic applications of curcumin, the yellow pigment that is present in turmeric, in cascade reactions, magnesium, application of magnesium bromoform reagent system for introducing tribromomethyl and also dibromomethylenated groups in various electron deficient alkenes, and then application of this sulfonyl phthalate as a 1,4 dipolar synthon for the synthesis of various fused and spiro carbocycles and heterocycles. Then in collaboration with a French group, we are working on application of carbon nanotube metal nanohybrids as heterogeneous catalysts in various organic reactions. We also have interest in various Michael initiated ring closing reactions. So yeah, this is my group, the latest picture, this is the last year's picture. And the students who contributed to this program on energetic materials are here, Bichismita Sahu, woman. So Bichismita is at NCPOR, Ahmedabad. Woman is a faculty in Finland, and Narasimham is in a company in Hyderabad. Guru Raja is faculty at Central University, Gujarat. Sohan is postdoc in the US, and she is still continuing her PhD, Tejasri. So I must thank all my students who contributed to this project, my collaborators, especially Professors Chowdhury and Kumpakarna, and also Sudarshan Kumar from the aerospace engineering, and their students. Some of them got Best Thesis Award for work in this area, and collaborators Dr. Nainan, who retired long ago from ESSC, Dr. Verghese and Dr. Reshmi, and collaborators from DRDO, Dr. Arvind Kumar, Nandagopal, and Rohit, and most of the facilities we have in our IIT. And I must thank the funding agencies, ISRO and DRDO, for their support. Thank you very much.
Very nice talk.
Thank you.
Now these energetic materials are thermodynamically very unstable, but must be kinetically stable, right?
Yeah.
So have you looked at the activation energy barrier or something like that?
Yes, we have calculated the bond dissociation energies of those cage compounds, and we found that the strained rings break first, especially the cyclobutane ring. We found that. Yeah. So we have evaluated the decomposition pathways. I mean, since the time is short, I could not present any of that. And some of the functional groups break first, like nitro. That also we have observed.
How do you address the concept of decomposition pathways?
Yeah.
Because that's something which is very important for all these compounds.
Yes, so that is why we have the hydrocarbons as such do not undergo decomposition that easily. So we have introduced the energetic groups like nitro, azido, etc. And we found that the energetic groups first break away from the cage, and if it's homolytic decomposition, a radical would be generated, and then that would trigger the decomposition of the cage. Especially the highly strained rings break first. So there is an activation energy for decomposition.
The concept which I was trying to understand was, is there always a unique pathway for that?
A unique pathway? No. It changes depending upon the functional groups attached to those compounds. Yes. So each compound we evaluate.
I have a layman's question.
Yeah.
You were talking of both liquid propellant and solid propellant based
Right.
on the same cage compounds.
Yeah.
Do
Yeah.
you have any general comment on liquid versus solid?
Yes, some of the compounds are solids and some others are liquids. But the liquids are highly viscous liquids. So we could add that to solid propellant combination as well, like APH TPB.
Physical properties are quite similar.
Yeah, quite similar. Yeah, these are not free flowing liquids like the RP1. RP1 is like kerosene, refined kerosene or jet propulsion fuel.